So everyone, today we will solve a problem about an LC circuit and I demonstrate it using a simulation, pulse-type simulation. So we have capacitor of 1 microfarad and is charged to 40 volts. It is then connected to a 10 millihenry inductor and we need to find the maximum current in the acceleration. How we will find this maximum current? First, I want to solve this problem using PRADA structure. So let me write all like pattern recognition, abstraction, and decomposition. Then I will explain the problem step by step. So pattern recognition, that is LC oscillation problem, and the energy is conserved and oscillates between capacitor and the inductor. Abstraction, we ignore resistance because we assume the circuit is idle, so there are no energy losses. Then decomposition. So first of all, we separate the system into capacitor energy and the inductor energy. Algorithm. Now we apply just energy conservation to find the maximum current. So now let me show the algorithm, how to solve it. So as I said, first it's a capacitor energy. We know that it's 1 divided 2 and squared. So that was our first part, like energy stored in the capacitor. Now we say that its energy is conserved. So and say it oscillates between capacitor and inductor. So energy in inductor, it will be 1 divided 2 L multiplied I squared. So current in here, it will be our maximum current. So we say that the energy is conserved. That's why energy that's stored in capacitor and the energy stored in inductor, they will be equal. Now we will just put the values, put the numbers, then we will find our maximum current. So it will be again our I maximum equals square divided inductor and square under the square root. So now let's put the numbers. So capacitor, it was 1 multiplied micro, it is 10 power minus 6. We have 40. It's divided. Inductor is 10 millihenry. Now let's calculate it. So here are calculations. So it's we can write it as 400 milliamperes. So it's our maximum current in this problem. So we find Imax. Now, let me show this in its circuit, its simulation. I forgot about that. Sorry. So that's our how it like its simulation. It's our capacitor and it's our inductor. Now let's start our simulation. So it's how it's like current flows through the circuit. It's here it is graph as you see. Maybe if I will decrease its oh it's no, let's see the maximum current. So let me slow it, maybe then we will see. Oh, look at this. Look at their graph below the circuit where it says катушка индуктивности, and then you will see that our current its maximum 399 that we it's closely number that we find that we solve it. So as you see, we solved the problem correctly. Yep. Now let me add speed of this. Speed of current. Oh my god, as you see, that's simulation. Now, next, let's move to the next problem. Here our next problem. In this problem, we are given a series LC circuit powered by an AC source. The inductance is 8 millihenries and the capacitance is 89 microfarads. The source provides an RMS voltage of 6.788 volts at the frequency of 50 Hz, and we are asked to determine the RMS current. And also we should find the frequency that produces maximum current, which corresponds to resonance. So, I also use PRADA structure to solve this problem. So first of all, let me write all like pattern, recognition, abstraction, decomposition. Then I will explain the problem step by step. So here are PRADA structure. So as a given, it's a series LC circuit with a alternating current source. And we should know that K pattern is that current depends on the difference between inductive reactance and capacitive reactance. So then the maximum current occurs at resonance, and the resonance happens when these two reactances are equal to each other. So our abstraction it's that we only focus on inductance, capacitance, frequency, and the voltage. We ignore the physical light and focus on the reactance and impedance behavior. The composition, first of all, we will calculate the inductive reactance and capacitive reactance. Then we will find impedance. Then we will calculate the maximum current and the frequency that will determine the resonance frequency. So now let me show the algorithm like that followed our decomposition. So let us say let's find inductive capacitance. So inductive, let me change the color of it. So first, how we will find? We will multiply angular velocity to the inductance. So how to find angular velocity? Well, we know that angular velocity is 2 pi multiplied frequency. It's a given frequency, okay? So now, if we will calculate it, do not hesitate to stop the video and calculate it by yourself. I already calculated, so I will write the numbers, okay? So it's probably 2.5 ohms. Next, we should find this one. Do you remember the formula? Yes, it's 1 over velocity multiplied capacitance. So, also, I already calculated it, so it will be almost probably 35.7 ohms. Now, let's find impedance. Third one, yes. Equal minus 6c. So it will be 33.5 ohms. Let's move on. So we find the impedance now. We just find the current by the Ohm's law. Let's say the Ohm's law. Ohm's law say that we can find it current by dividing voltage to the impedance. So our voltage is given. It is 6.788 divided this number 33.2. Then we will get the answer. It's 0.22 ampere. Or we can write it as 204 milliamperes. Now let's move on and find resonance frequency. So, as you know, as I said, we find it this resonance happens when our inductive reactance and the capacitive reactance are equal. Oops, no. L multiplied. Wait, it's equal. C. So let's calculate it as. So if we will calculate it, we get this number like 1 over L C, and our angular velocity equals C. Also, our angular velocity, we know that it equals 2 pi. Yes. Then if we will calculate it, it will be 1 over 2 pi, and as a square root is LC. I think you probably know this formula from the period. Yeah, it's 2 pi multiplied on the square LC. It's our period. Now, let's put the numbers and calculate our frequency. 2 pi, our L was what? I forget it. Our L was 8 and 98. Then 8 meters milli multiplied 89 10 power of minus 6. So I said, so it's, if we calculate it, it's probably 188.7 hertz. Now, so it's a solution. Now let me show this on simulation. Yes. Here it is simulation. Yeah, I know that it looks a little bit not perfect, but actually it is the same circuit. Like, let's start it. So, as you see in the circuit and the simulation, the inductor stores energy in a magnetic field, and the capacitor stores energy in an electric field. So these two elements, this inductor and the capacitor, are continuously exchange energy, which creates accelerations in the circuit, like on the previous problem that we solved. So in the graphic, like here, you can observe the graphs. Here, the voltage across the capacitor, the inductor, and the source. And we can see that the signals are sinusoidal, but they are not perfectly aligned in the time. Then the capacitor voltage reaches its maximum. The current in the circuit is minimal, and when the current is maximum, here it is, the capacitor voltage is minimum. So this shows us that the energy is constantly transferred between electric and magnetic forms. And now, if we change the frequency of the source, the behavior of the circuit changes. Let me show it. Now we have like 80 hertz, maybe we'll 90. So, so when at a certain frequency, the current becomes maximum, and this is a resonance. Yes, as you see, the graph is changed. Now maybe we'll put more frequency, maybe 150. Why not? Oh, you see how the graphs are changing? So it's what I'm talking about. Like if we change the frequency of the source, the behavior of the circuit changes, as you see. So thank you for your attention. Bye bye.